Welcome to tutorial number 10. In this tutorial, the final tutorial of this course, our discussion is on tiled chip multicore processors and NoC design principles. We will work out few problems related to these topics, which will help you in getting a deeper clarity on the concepts learned during the lecture videos. The first question is on an NoC router does the following functions: virtual channel allocation, which is represented by VA, then route computation, buffer write, switch traversal, switch allocation. So, these are some of the functions that happen in an NoC router. Now, we have to write the order of events, in which order these are happening. So, this is the internal architectural diagram of an NoC router. In a two-dimensional mesh NoC, each router is connected to 4 of its neighboring routers, and there is a link that is connecting to the local processing element. The flits will travel through these ports and reach these virtual channels. These are called buffers. So, buffer write is the first operation that happens. In every cycle, the flits that are residing inside the buffers, they are being routed. So, you apply the corresponding routing algorithm to find out what is the desired output port. So, routing computation is the second operation. Once route computation is over, the very next process is flow control, the process by which you reserve a buffer in the downstream channel. Let us say if a packet gets east as the output, then in the east neighbor I have to reserve a buffer for this packet, and that reservation is known as virtual channel allocation. For all packets who got virtual channels, now we have to assign them the output ports. So, there may be cases that multiple packets might have got the route, same route, or different packets are competing for the same port, and in that case only one can be permitted per port. So, we can permit only one port through east, one through west, north, south and east at most. So, switch allocation is the process by which whenever there are multiple packets competing for the same output port, which is the winner, that is decided by the switch allocation algorithm, and then the flit travel through the switch, and then at the end it is traveling through the link. So, the order in which it is being done is buffer write, route computation, virtual channel allocation, switch allocation and switch travel. This many things are happening inside the router, and this is the link traversal. So, the moment it comes out of router, then you are already in the link. So, link traversal is the final stage. We move on to the next question. A cache miss request packet P1 with a destination address 13 is injected into router 7 in a 4x4 mesh network on chip that uses XY routing. State whether each of the following statement is true or false. So, these are some statements that is being given. So, we are talking about a 4x4 mesh NoC. So, we have to be familiar with the numbering. Let us say this is the 16 core processor that they are talking about, in which the routers are organized in a mesh fashion, in a 4x4 mesh fashion, and always numbering is from bottom left all the way to the top right. Now, here we have a packet whose destination is 13 is injected into router 7. So, from router 7 there is a packet moving into 13, and when you apply XY routing, this is the way in which the packet goes from 7 to 13. It is a cache miss packet. So, there is a cache memory that is associated to 13, and you go and search in the cache, get the data, and then a reply packet is created that will travel all the way from 13 to 7. So, your request packet is going through the red line, what is being shown as per XY routing, and the reply packet is coming through the blue line as shown in the diagram. Now, there are few statements given from which we have to say whether they are true or false. P1, that is a packet that we are talking about, while moving through the NoC takes a 90-degree turn at router 15. So, the P1 is moving through the red. So, it never travels through router 15. So, the question of whether it takes a 90-degree turn at router 15, that means it is actually wrong, it is false. Now, P1 passes through router 9, we can see that it is passing through router 9, so that is true. P1 takes 5 hops to reach the destination. So, from 7, it takes 1 hop to reach 6, 2, 3 and 4. It takes only 4 hops to reach destination. So, P1 takes 5 hops to reach destination, that is also false. The reply packet of P1 moves through router 14. You can see that the reply packet is traveling through the blue arrow. and the reply packet is moving through 14. So, this is true. Neither the request packet nor the reply packet passes through router 10. We can see that the request is passing through 7, 6, 5, 9, 13 and the reply is coming from 13, 14, 15, 11, 7. So, none of them are touching 10. So, neither the request packet nor the reply packet passes through router 10. That is actually true. So, we have first sentence false, second one is true, third is false, fourth is true and fifth is true. We now move on to the next question. Consider a 25 core machine in which cores are organized as regular square mesh topology. A packet P1 is generated from core number 18, this is core number 18, destined to core number 6. The system follows minimal north-last routing. How many unique minimal paths are there from 18 to 6? So, I am talking about a packet that starts from 18 to 6 in a 5 by 5 mesh interconnect. So, how will you know it is 5 by 5? It is a 25 core machine and they are organized as square mesh topology. So, 25 has to be organized as square and this is the way how it is organized. You have a 5 row and 5 column format and the numbering is 0 is there in bottom left corner and 24 is there on the top right corner. Now, we have to understand what do you mean by north-last, it's north-last routing, minimal north-last routing. So, minimal north-last routing say that first of all the minimality condition at every hop the packet should reach one hop closer to the destination, that is called minimality. If that condition is ensured everywhere, we can call the algorithm as minimal. Now, the second one is called north-last. So, if a packet wanted to move to the north direction at any point of time, then it has to be done at the end. That means transition towards south, east and west has to be taken and then only you can take a north. The moment you take a northward direction movement, then no other turns are being permitted. So, first thing is here you are talking about minimal. That means my packet can travel only in this quadrant from beginning. So, it cannot think of the routers which are there in the edge and corner. So, from 18 it has to go either to 17 or to 13. Now, north last. So, since my destination is on south of me, there is no need to go to the northward direction. So, there is no restriction that is being applied. Had the destination be in 20 for example, then I can travel from 18, 17, 16, 15 and then only I can take north transition. That is called north last. So, in this case we are not talking about 20. Anyway, I am just giving an example of how it works. So, from 18 we have possibilities. One is I can take a possibility like this, that is my first possibility. Second possibility is I can take an option like this, because there is no restriction in taking an east, south or southeast, whatever order it is. We have restriction only in moving towards north, that is called north last routing. And the third possibility is like this. Then we have a possibility like this and then the possibility is like this and the last possibility is like this. So, we have 6 options: 18, 17, 16, 11, 6, 18, 17, 12, 11, 6, 18, 17, 12, 7, 6, 18, 13, 12, 11, 6, 18, 13, 12, 7, 6, 18, 13, 8, 7, 6. So, we have total of 6 unique paths from 18 to 6 with minimal north-last routing implemented. Now, the next question is on switch arbitration. An input buffered NoC router R that uses age-based switch allocation scheme. So, age-based means higher age has higher priority, and XY routing receives 4 packets at a given clock cycle. The details, that is packet number, age, source and destination of the packet are, let us say we have a packet P1 2 5 15 2, P2 is 1 10 0, P3 is 3 7 11 12 and P4 is 2 9 3. Let us try to understand what this representation is. You are talking about a router. State whether each of the following statement is true or false if R is router 10 in a 4 by 4 mesh interconnect. So, to a router 10 in a 4 by 4 mesh NoC, we are getting 4 packets in a given clock cycle. Packet P1, it has an age of 2, it is coming from 15, it is in the process of going to 2. So, 15 and 2 are the source destination. Similarly, P2 is coming from 10 going to 0, P3 is from 3 going to, sorry, P3 is from 11 going to 12 and P4 is from 9 going to 3. So, the age of the packets are also given. Now, let us try to understand how these packets are coming. So, we are talking about router number 10, these are the packets. Now, from where P1 is coming? P1 is coming from 15, it is going to 2. So, P1 coming from 15, it is going to 2. So, this is the process by which P1 comes and it wants to go to 2. That is all about P1. Now, P2 is coming from 10 and it is going to 0. So, P2 is a newly created packet coming from 10 and it is going to 0. That is a condition of P2. Now, P3 is coming from 11 and it is going to 12. So, P3 is coming like this and it is going to 12. That is called P3's case. And finally, we have P4 which is coming from 9 and going to 3. So, the packet coming from 9 and it is going to 3. That is all about P4. So, these are the 4 packets that is coming. So, your P1 is entering router 10 through north input port, that is what is being shown there, north input port. Now, P2 is coming from local input port and then it is going towards, or it is trying to go towards western direction. P3 that is coming from east direction and trying for west, and P4 is coming from 9, that is 9 is connected to west. So, it is coming from west input port and trying to move towards east. Let us try to write all these. So, packet P1 has an age of 2, whatever data that is been given, source is 15, destination is 2, it is coming through north input port. P2 is having an age of 1, it is coming from 10 itself, that is it is coming from the local port. And P3 age is 3, source is 11, destination is 12, that means it is coming from east input port. And P4 age is 2, source is 9 and destination is 3, so it is coming through the west input port. Now, when you apply XY routing at router 10, if you have a packet that is looking for destination 2, then south is going to be its output port. Now, in 10 if you wanted to go to 0, 0 is here, but if you apply XY routing, first I have to travel in X direction. So, west is what I want. Similarly, if I wanted to go to 12, that also will be possible only through traveling westward direction. So, a travel to 0 and travel to 12, anywhere from 10, it is a westward movement as per XY routing. And the last packet P4, destination is 3, and to reach 3, I have to take an eastward movement. Now, if you look at, we have 4 packets, out of which the first one is looking for south, second and third is looking for west, and the fourth packet is looking for east. So, since there is nobody for south, south will be granted for P1. Since there is nobody competing for east, there is only one, then east is also granted. But we can see that there are 2 of them looking for west. Here is a place where switch arbitration happens. So, what we have learned here is, we have a couple of packets coming together and we are there in an NoC router, and we find out through which input port they are coming, and based upon the destination address, we have to find out what is the desired output port. If there is only one packet that is competing for this particular output, then that is been granted. But if there are more packets looking for the same output port, then we have to pick one among them, and that is called switch arbitration. In this case, arbitration is done with the help of age based priority. So, that packet which is having the higher age, that is being given preference. Now, we have a case where 2 packets are competing for the west output port. So, one is packet P2, other one is packet P3. So, if you carefully look, you know that packet P2 has an age of 1 and packet P3 has an age of 3. So, P3 is being given the west port and P2 is asked to buffer. So, this is the status that we have. Now, based on these observations, there are certain questions that is being asked. P4 enters R through its north input port. So, the statement is P4 enters R through its north input port. So, P4 is entering through the west input port. So, this statement is false. The second statement is both P2 and P3 wanted west output port at R. So, P2 and P3 they both wanted west output port at R. That is true. Now, at the end of switch allocation phase, P4 will remain in its buffer. So, this is the question, but P4 actually got east output port. So, the statement that it will remain in the buffer is false. And then there exists an output port conflict between P1 and P4. So, P1, this output port conflict means they both are requesting for the same. So, P1 is requesting for south and P4 is requesting for east. So, there is no conflict. So, the statement there exists an output port conflict between P1 and P4 is false. And moving on to the last one, at the end of the switch allocation phase, P1 gets south output port. So, P1 it is getting the south output port. So, that is true. So, in this case, based upon the routing that has been happening and the switch arbitration policy, few statements are given and we are checking whether they are true or false. Now, the next question is on traffic patterns and packet latency. Consider an 8x8 mesh NoC that use single flit packet scheme. Consider a 3-cycle router and a 1-cycle link for NoC that uses XY routing. 3 packets P1, P2, P3 were generated from routers 6, 24 and 50 respectively. So, we are talking about an 8x8 mesh NoC out of which 3 packets are generated, and here they are telling that in the router will take 3 cycles. So, we have learned different functionalities of the routers like buffer write, route computation, virtual channel allocation, switch allocation and switch traversal. Together all these 5 operations are being divided into 3 cycles and it take 1 cycle through the link. So, moving from one router to another, it will take 3 cycles inside the router, that is a processing time inside the router, and 1 cycle in the link. So, total a hop will take 4 cycles. It is using XY routing. Now, we are talking about 3 packets here P1, P2 and P3 are 3 packets which are starting from 6, 24 and 50 respectively. If packet injection and ejection take 2 cycles each, so the process by which a local tile create a new packet and inject into the local port, that is called injection, and the process by which a packet is removed from a router to the tile, that is known as ejection. So, at the source the injection happen, at the destination the ejection happen. So, both injection and ejection process in this problem are taking 2 cycles each. Now, we are asked to find out what is the latency of P1, P2 and P3 if the packets follow a transpose traffic pattern and a bit complement traffic pattern. So, this is the 8x8 mesh that we are talking about, ranging from 0 all the way up to 63. Now, this particular table, you look at packet P1, its source is 6. Now, there are 2 traffic patterns that is been mentioned. The first traffic pattern is called a transpose. So, transpose means if a packet that is starting from row I and column j, in transpose pattern, the packet is going to row j and column I. So, interchanging the row number and column number. So, a packet from 1 will go to 8. Now, a packet 10 will go to 17. A packet 7 will go to 56. Similarly, a packet 61 will go to 47. So, this is just to give a picture about how the transpose pattern works. Now, in this case, we are being given 3 packets P1, P2 and P3, and your packet P1 is starting from source S from 6. Packet P1 is starting from source 6. Now, as per transpose pattern, from 6 the packet should move to 48. So, 48 is a transpose node. All packets generated from 6 are going to 48. That is why it is. So, this kind of transpose is a synthetic traffic pattern. We are artificially creating traffic, meaning we are mentioning where is the source and where is the destination. So, all packets from 6 are moving into destination 48. Now, what is the peculiarity? From 6 to 48, it takes 1 hop to reach 5. So, 2 hop, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It will take 12 hops from 6 to reach 48. In each of the hop, we are going to take 3 cycles in the router and 1 cycle in the link. So, total 4 cycles are needed to complete 1 hop. Plus, you have 2 cycles for injecting the packet at 6 and 2 cycles for removing or ejecting the packet at 48. So, you have another 4 more cycles. So, the equation is latency of a packet is defined as number of hops into 4 plus 4. This second 4 will take care of injection as well as ejection. So, 12 into 4, so 12 hops is the packet has to take. 12 into 4, 48 plus 4, 52. So, it takes 52 clock cycles for a packet starting from 6 which follows a transpose pattern. Similarly, packet P2, the source is 24. Now, when the source is 24, the destination as per transpose pattern is, destination is 3. We interchange row and column. So, all packets on 24 are travelling through 3 and this is the path by XY routing it will take. So, how many hops are there? 1, 2, 3, 4, 5, 6. So, we have 6 hops, 6 into 4, 24 plus 4. So, it takes 28 cycles for this packet. And similarly, we have P3 that is starting from 50 and as per transpose pattern, the destination is 22 and it takes 8 hops, 1, 2, 3, 4, 5, 6, 7 and 8. So, 8 into 4 plus 4, total 36 cycles are needed for a packet to reach 22 from router number 50. For the same question, rather than transpose pattern, they are asking for a second traffic that is known as bit roof or bit complement traffic. In the question it is mentioned, we have to find for bit complement traffic as well. Packet starting from 6, the destination is 57. Now, we have to find out how a bit complement destination is there. In the case of a transpose pattern, we have to find the transpose node. So, in the case of bit complement, our source here it is given as 6, packet P1, the source is 6. So, when you write 6, this is the binary value of 6. We complement this, so we get this as the complement and this correspond to, so packets from 6 are moving to 57 when you follow bit complement traffic pattern. Similarly, packet 24. So, if you look at what is the complement node for 24, 24 is represented by this is 24. Now, its complement is so it is 32 plus 7, 39. So, as per bit complement pattern, packets generated from router 24, the destination is 39. Similarly, if you write 22, you can find that the destination is going to be 13. So, how are you going to assess it? So, packet P3 is starting from 22. So, for the case of packet P3, the source is given as 50. Now, source of 50 means 50 is defined as 32 plus 16, that is 48, this is 50. So, if you complement and this indicates 13. So, a packet that is starting from 50, the destination is 13. Now, the problem is same like what we discussed previously. So, the whole purpose of using transpose and bit complement is to understand what is a destination. So, in transpose it is interchanging of I and j. In the case of bit complement, you write the binary value of the source node and then complement it in binary and that is going to be the destination. So, packet from 6 will go to 57, 24 will go to 39 and 50 will go to 13. Now, from 6 to 57 there are 12 hops, you can see that 6 all the way to 57 and as per XY routing it is going like this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, 12 hops, 12 into 4 plus 4, that is for injection and ejection, that gives you 52 cycles. Now, coming into the second one from 24 to reach 39. So, this is 24 and I have to reach 39. So, 1, 2, 3, 4, 5, 6, 7, 8. So, it is 8 into 4, 32 plus 4, 36 cycles and the last one is moving from 50 all the way to 13. So, this is 50 and 13 is given here. So, 1, 2, 3, 4, 5, 6, 7, 8. 8 into 4, 32 plus 4, 36. So, in this way, we are able to find out how much a packet is taking to travel through the network. So, based upon the source and destination and the number of hops it has to take, we have to apply this equation. The latency of a packet is defined as, it depends on number of hops, and in each hop it will take 4 cycles to complete, and the initial overhead of 2 cycles for injecting and the final 2 cycles for ejecting this packet. Now, let us move into TCMP address mapping, tiled chip multi-core processors. So, this is a typical question which covers all the aspect of cache memory and NoC together. Consider a TCMP system in an 8x8 mesh NoC, where each tile consists of a superscalar processor, a private L1 cache and a shared distributed L2 cache. We have seen it in the lecture. Each tile consists of a processor, L1 and L2 cache. But the L2 cache is shared and distributed. Let T0 up to T63 correspond to the tiles. The total L2 cache on the chip is 16 MB. So, I have 16 MB of L2 cache that is scattered across 64 tiles. And each L2 uses 64 byte blocks, and the L2 cache is 16-way associative. Each L2 cache on chip has all the 16 ways of the set assigned to it. The L2 cache memory per tile division is such that total sets in L2 cache are uniformly partitioned across all tiles in a sequential fashion as per SNUCA policy. SNUCA means static non-uniform cache access policy. So, you have total of 64 tiles are there. Now, the 16 MB of L2 cache is being scattered across all the tiles. So, each tile will be having a uniform share, and this policy is known as the SNUCA policy. The system used 32-bit physical address. Now, tile 52 generated a cache miss for an address that is been given, and tile T3 generated an L1 cache miss on address. So, 2 L1 cache miss addresses are being given. Now, we have to find out from which tile you are able to find the corresponding L2 cache mapping. Where are these addresses mapped in TCMP? So, let us rephrase the most important aspects of the question. I am talking about an 8x8 mesh NoC, and the property of L2 cache is it is shared distributed L2 cache, 16 MB of L2 cache, which is 16-way associative and 64 byte block. We are using 32-bit physical address, and T52 is generating an address 0x34120568, and T3 is generating another address to 0xA02359A0. Where are these addresses mapped in TCMP? So, first is we have to find out the total number of sets in L2 cache. It is 16 MB. So, cache size 2 power 24 bytes divided by block size. We are talking about blocks of 64 bytes. So, it is 2 power 6, and associativity is 16. So, altogether I have 2 power 14 sets that is scattered across 64 tiles. So, to represent a set number, we require 14 bits index. Now, if you look at the address, I am talking about a 32-bit physical address having a 14-bit index. This is cache memory principle what we have learned. So, the 32-bit address is divided into 14 bits index, and since the block size is 64 bytes, which already mentioned, the last 6 bit is used for offset. So, that makes 14 plus 6 is equal to 20, 32 minus 20, I have a 12-bit tag. Now, I have 2 power 14 sets are there, which is scattered across 64 tiles. So, the most significant 6 bit will tell you which is the tile number, and the last 8 bits of the set index will tell you within a tile I can host total of 256 sets. So, what is the set number? So, this is the question. So, in this case, the system used 32-bit physical address. Tile T52 generated a cache miss for the address. So, it is 0x34120568. So, we have already found out the split up of the address. Now, this is the address that I am talking about, out of which the one that is been shown in red, 0x341, it is a hexadecimal value. So, this 12 bits will represent my tag, and the remaining 20 bits will represent my index and offset together. Let me expand what is written in this blue color, 20568. So, hexadecimal 2, 0010, this is 0, this is 5, this is 6, and this is 8. So, the green portion indicates a set number. Now, in the set index number, take the first 6 bit. So, the first 6 bit is 001000, and this is the set number within that tile. So, what is seen in the yellow color within this rectangular box that tell you it is tile 8. That means this miss that is generated from tile 52. So, we have an address from 52 which upon looking in L1 cache encountered a miss. That means then you have to go and fetch it from L2 cache, but L2 cache is not a private cache for tile number 52, it is a shared distributed cache. So, the request is going from 52 all the way to 8, and what we have found out is it is tile 8. We do not know where it is. By looking at the address, looking at these 6 bits will tell you where the request is going, and the cache block will be returned from 8 to 52 by XOR routing following this path. Now, tile T3 generated an L1 cache miss on the address 0xA02359A0. The same process is being applied, where the red portion indicates tag and the blue portion indicates index and offset bits together. I am trying to expand the index and offset bits. So, it is 3, this is 5, 9, A and 0. Extract the first 6 bits, and the first 6 bits will give you tile 13. So, this is the request that started from tile T3. So, T3 gave a cache miss, an L1 cache miss, and this address is mapped into tile 13. So, this is the way how the packet is going. So, this particular problem is a classical example of how generally a tiled chip multi-core processor works. Generally, we have many such processors which are there in these tiles, and each of these tile houses a processor, a private L1 cache from which the processor directly interacts. So, the fetching operation happens from this private L1 cache. Once in a while, you will miss in this cache. Then we know that when you miss something in L1 cache, you have to go to L2 cache and bring it. But L2 is not located in one place. In the case of TCMP architectures, the L2 cache is shared and distributed. So, from the address, few bits in the address, the physical address will tell you which tile this particular L2 cache is located, or L2 address is mapped. And this policy is called SNUCA, Static Non-Uniform Cache Access. So, divide the address in all these problems, divide the address into tag, index and offset. The index bit will tell you what are the total number of bits reserved for the L2 cache set, but L2 cache set is scattered. So, the most significant bits will tell you where is the tile or which tile is being mapped, and the least significant address bits of the index will tell you within the tile what is the set number. So, once you extract this most significant bits of the set index, it will tell you the mapping, and from that particular tile a packet, an NoC packet is being generated, and in the previous question we have seen how much cycles it will take for the packet to move. So, this is a classical combination of the processor, the cache and NoC together. That is what we are trying to achieve in this course, in the advanced computer architecture course, how the concept of processor, and we started with pipelining, we start from fetching from a memory, and this fetching can sometimes result in a miss, and when you miss you have to go to the next level, and now the levels are scattered. So, whole concept that we learned throughout this course is being used in this particular example. So, these are very important. So, kindly go and refresh these kind of questions more. With this we come to the end of this tutorial. So, all the tutorial sessions are over. So, by this time our entire course, which is spanning across 8 weeks, there were tutorial sessions, there were Gem 5 practice sessions. So, altogether these lecture videos, which is complemented by the tutorial session, will give you enough exposure in understanding the advanced computer architecture concepts. There are few more courses in line with this related to multi-core architectures, cache coherence and all. So, there will be more MOOCs courses in this direction. So, if you find these kind of topics interesting, I urge you to continue studying in this fashion. Thank you.